Now we are going to discuss about the perturbation theory. It's a time independent perturbation theory, and we are considering a non-degenerate case. So this is a stationary time independent non-degenerate perturbation case. Now let us first consider the Schrodinger equation, and which is given by H psi is equal to W psi, where H is the perturbed Hamiltonian and W is the perturbed energy level. Psi is the perturbed stationary wave function. Now H may be split into two parts. One is H naught, another one is H prime, H naught plus H prime. And this H naught is unperturbed Hamiltonian and H prime is a perturbation. And H prime usually it is very small when compared with the H naught. Now the H prime is small. This suggests that the psi can be expressed as some of these few terms, which is psi naught plus lambda times psi 1 plus lambda square psi 2 plus lambda 3 psi 3. This is not a square, this is only a superscript. So lambda 2, so this is a square, and the superscript this is a square. Lambda square and lambda cube. This is the order, and the psi 1, psi 2, psi 3. These are the subscript. And W is equal to W naught plus lambda times psi 1 plus lambda square psi 2 plus lambda power 3 psi 3, and this is the lambda power 1, lambda power 2, lambda power 3. Psi naught is the unperturbed wave function, W naught is the unperturbed energy value. Now here we replace H prime by lambda H prime. Then the different order of the perturbation approximation are given by the coefficients of the corresponding powers of lambda. In the final result we can set lambda is equal to 1. So now substitute the psi and W and H prime in the wave equation 1. Here H naught plus lambda H prime into psi naught plus lambda times psi 1 plus lambda square psi 2, etc. So this is left hand side. The right hand side W naught plus lambda W1 plus lambda square W2, etc. into psi naught plus lambda psi 1 plus lambda square psi 2. So this is the right side. So this is equation 3. Now let us equate the powers, equal powers of lambda. First we choose the lambda power 0. We equate the lambda power 0 on both sides of that equation 3. We get H naught minus W naught psi naught is equal to 0. So this is equation 1 we are getting. Then if we equate the power lambda power 1 on both sides of that equation, we get H naught minus W naught psi 1 and is equal to W1 minus H prime psi 0. So we are getting equation 2 if we equate lambda power 1 on both sides of that equation. Similarly, if you can equate the lambda power 2 on both sides, we get H naught minus W naught psi 2, which is equal to W1 minus H prime psi 1 plus W2 times psi naught, which is equal to 4.3. And if you equate the lambda power 3, the coefficients of lambda power 3 on both sides, you will get the equation 4.4. So in general, if we equate the lambda power s on both sides, then that equation is H naught minus W1 psi s is equal to W1 minus H prime psi s minus 1, and this is a W2 psi s minus 2, W3 s ws minus 3, and so on, ws psi naught. So you get the equation 4.5. Now let us put the psi naught. The psi naught is one of the unperturbed eigenfunction. So for convenience we put psi naught is equal to um. This is the unperturbed eigenfunction. and W naught. This is the unperturbed energy again. So EM. W naught is we put the EM. This is the unperturbed energy level. Then we observe these two things. One is psi naught comma the inner product of psi naught with any psi s is 0 if s is greater than 0. So s is equal to 1, s is equal to 0, this is psi naught comma psi 0. So this is an orthonormal function. So this is 1. Otherwise for all s greater than 0, the equation 6 is valid. Psi 0 comma psi. So this is the inner product of psi 0 with any psi s where s is greater than 0. The second thing is we take this one. Suppose this is a omega operator. So integral over psi alpha star omega operator psi beta. This is the volume element d cube r. So this is equal to omega operator star psi r whole star into psi beta of r d cube r. So this can be expressed in this form. So in this integral notation you can write like this, or in the direct notation, omega this is operating on the ket, this is the bra beta, omega operating on bra beta, so omega operating on this is the ket symbol, this is a direct symbol, this is your ket symbol, and this is the conjugate of this one, we call this is a bra symbol. So omega operating on beta gives beta prime, and this omega operating on the conjugate, the bra function gives alpha double prime. So this is omega, the alpha beta. So this is equal to, if you operate this side, this will be alpha double prime beta, and it can operate this right side, you will get beta prime, so alpha beta. So they all are equal. So you can, this is a direct notation, and this is the integral representation. So the inner product of psi naught on the right hand side of equation 4 is 0 in each case, and with the help of equation 5 and 6. So this is 5 and this is 6. So with this help, Ws is equal to, so from equation 4.5 you take a psi 0 comma h prime psi s minus 1 divided by psi naught comma, this is the inner product of psi naught with the psi naught. This is equal to, this is psi naught is just so psi naught is the because it's the unperturbed this is an eigenfunction, and this is psi s minus 1, this is h prime. So this is for any s greater than 0, this is the expression, this is equation 7. So from equation 5, using equation 5 and 6, and from equation 4 you can obtain this expression. So if you take a 4.5 and using 5 and 6, we get the equation 7. Then now let us prove this equation 7. So equation 4.5, so this is equation 4.5, this is the expression h naught minus w naught psi s is equal to w1 minus h prime into psi s minus 1. So this is here psi s, this is related to psi s minus 1, the lower value psi s minus 2 up to psi 0. Now you make an inner product with psi 0. So this we are making an inner product with psi 0 of this equation. So you will get, this is psi, you will take the term by term. First term, this is w1 psi 0 psi s minus 1 minus, here this h prime, so psi 0 psi s minus 1. So alright. Then Next one is this is the second term. This is W2 psi s minus 2 and this is psi s. And so on. Finally, you get this term. Actually, you have intermediate terms. So finally, this is Ws psi 0 psi c. Now, this is H naught acting on psi naught is equal to W naught. So the first term is W naught psi 0 psi s, and this is minus into, and the W naught can be taken outside, and this is psi 0 psi s. So according to the equation 2, s is more than greater than 0. This is a normal, orthonormal, psi 0 psi s. So this is equal to. So this and this gets cancels because this is W and this is W0, so both terms gets cancelled. But here psi 0 psi s minus 1, this is orthonormal, so this is 0, and you have the term psi 0 h prime psi s minus 1, and similarly if you take a W2 outside, and this is inner product of psi naught with the psi s minus 2, both are orthogonal, so this is 0. As per we have already mentioned that this, if psi 0 comma psi s, the inner product of psi 0 with psi s is 0 for s greater than 0, so this is also 0. Similarly for all the other values, here there are some intermediate terms, they all are 0. So finally Ws psi 0 psi 0, but psi 0 is this is 1, because this is orthonormal function psi 0 psi 0. The inner product of psi 0 is 1. So this is a non-vanishing term, is Ws. All the other terms are 0. Here this term is 0, and this term is non-zero. So W is minus W psi 0 h prime psi s minus. So this is one term, and this is another term. All the other terms are 0. So if you take a psi s on one side and the other terms on the other side, so psi s is equal to psi naught. This is h prime, and this is the psi 0, and this is psi s minus. Now you put s is equal to 1. If you put s is equal to 1, you will get the first order correct. So s is equal to 1 means so psi 0 h prime psi 0. You will get this expression. This is since we are already mentioned, this is unperturbed eigenfunction, and the unperturbed eigenfunction we call this psi, and the ket of the psi m is the same as the ket of um. For convenience, we can put ket m itself. So both are having the same meaning. So you put replace psi 0 by this ket m, psi 0 by x. So just for convenience, we are writing this form. So h prime, and this is m. So now h prime is the expectation value of the unperturbed state, because this is unperturbed state m, this is unperturbed state. So h prime m. So this is the expectation value, and the expectation value of h prime for the unperturbed state. So this is your the first order correction. Now it is convenient to calculate psi 1. So this is the first order verb function psi 1 by expanding it in the terms of uk. So you put a psi 1 is equal to, this is the sum over n, a n of 1 un. This is equal to 9. This s is the summation over all the discrete set together with an integration over the continuous set of functions. Now substitute this equation 9 in your 4.2, we get a summation over n h0 minus w0 and a n of 1 un, which is equal to w1 minus h prime psi 0, which is equal to the psi 0 may be replaced by un, therefore w1 minus h prime into un. So if you substitute this equation 9 in your 4.2, we get equation 10. Now from the equation 6, you put s is equal to 1. We already mentioned that psi 0, psi 1 is equal to 0. Therefore, substitute equation 9 in the above equation, we get this is psi 0, comma, psi 1 is summation over n, an1 un, which is equal to 0. And this is psi 0, and here this can be split into two parts. One is you put the n is equal to m, that term alone is separated out, so m1 um. So and the remaining terms are an un summation over n, and here since we have taken one term, the mth term outside, the remaining terms are n is equal to not n. So there is a summation over all n except n is equal to n, because n is equal to n, that term is taken out separately. So this is equal to 0. So here the prime indicates there is a summation over all n except n is equal to n. Now here this is am1 that can be taken outside, since it is not an operator, it can be taken outside. This is psi 0 we have already mentioned. This is the unperturbed state here comma plus summation over n. Here again this is a u0, this is un, and this an1, that coefficient can be taken outside. That coefficient can be taken outside, an should not be equal to m. So this prime indicates n should not be equal to m. So this is u0 comma un, and they are orthonormal. Therefore u0 comma um is equal. So this term is 0 and this term is 1, and this is both terms is equal to 0. Therefore the possibility is am1 is equal to 0. So this coefficient is 0. Therefore the equation 10 becomes, so in that expression am1 must be 0, so that can be removed. So the remaining expression is an1, n should not be equal to m. So that term alone can be taken here, an1 h0 minus em un is equal to w1 minus h prime um. So this equation 10 becomes like this. Now here h0 un is equal to en un, because the unperturbed Hamiltonian acting on the eigenstate is the energy eigenvalue. Therefore the above equation becomes summation 1 prime an1 en minus em un is equal to w1 minus h prime into un. Now here multiply this uk star. So this is a complex conjugate. This is your complex conjugate, uk star, and integrate over all the space. So summation over n prime an, here en minus em is there. This is not an operator that can be taken outside. So there is an inner product of uk with un this side. The other side uk comma w1 minus h prime un. Now what is uk un? This is a orthonormal, therefore delta k. Only when k is equal to n, it is 1, otherwise it is 0. The other side, this term can be split into two parts, uk w1 um, and this is an inner product of uk with this w1 um, minus uk comma h prime um. So that this can be split into two equations. Now in this first equation, the w1 can be taken outside. So this is inner product of uk with um. Since k m are different, this must be 0. Here second term is minus uk comma h prime um. So this is minus uk h prime u. So this is 0. Here k must be equal to n. Now from this ak1, because k is equal to, so delta k n is equal to 1, so n must be replaced by k. So ak1 into ek minus em, which is the other side, minus uk comma h prime um, or the coefficient ak1 is equal to uk h prime um divided by, so this is ek minus em. If you write em minus ek, there is one negative sign here, already there is a negative sign, so that's cancelled. So the final result is uk comma h prime um divided by em minus ek, and this can be expressed in terms of the Dirac notation, k h prime m. So this is the expectation value of h prime, so not the expectation value, this is h prime, which is this is a k prime, this is k h prime m. Only when both the states are same, you can call this an expectation value, otherwise this is k h prime m divided by em minus ek, and here the k should not be equal to k. Now therefore what is your psi 1? We have already mentioned psi 1 is equal to summation over n prime and the coefficient a k1, this is the coefficient. So n h prime n divided by em minus en into um. So this is the equation 13 is the first order equation psi 1. This is your first order function. Now from equation 4.3, from 4.3 you have this expression w2 is equal to psi 0 h prime psi 1. You refer back the equation 4.3 with this expression, and here you substitute for psi 1 from equation 13, then this is psi 0 is already your m, because this is new m that can be expressed by draw m h prime, and this psi 1 is equal to this expression. So n h prime m divided by em minus en infinity. So you substitute this value here. Then this is your w. Yeah, this is n h prime. Now this is m h prime n and this is n h prime m. So that is the modulus of, because this is the one term is the conjugate of the other. So you combine these two, you can write a modulus of m h prime n whole square. So this is this term divided by em minus n. Here n should not be equal to m. So the prime indicates n should not be equal. So equation, this is the second order energy correction. This is the correction to the energy, the second order correction to the energy. So this is equation 14. So far we have calculated the first order correction energy, that is W1. So this is your first order correction energy. So the first order correction energy we have calculated, and the first order correction wave function, this is a this is your first order correction to the wave function. This is also important. And this is the second order correction to the energy. So the usually in the similarly you can calculate the other higher orders correction to the wave function as well as the energy can be determined. But usually in the examinations, net or gate examinations, and you are asked to find the first order correction energy as well as the second order correction energy and the first order correction to the wave function. That's why we are not taking the other part. The psi 2, psi 3 we are not calculating, but in principle you can calculate. Similarly, we are not interested in finding the W3 because W1 is small, W2 is still small, So the higher order terms usually we are not interested. Now we are interested in doing problems in perturbation theory. So usually we are considering one-dimensional box, the one-dimensional infinite problem. So which is one-dimensional box problem we are discussing. The next is we are interested in doing the linear harmonic oscillator problem. On the third, we are interested in doing the hydrogen atom problem. So we discussed the perturbation problems related to the one-dimensional box problem and the linear harmonic oscillator problem and the hydrogen atom problem. Now here, before doing this problem, now let us recollect some of the results, because once if you have these results in your mind, you can do the problems very quickly, because in the examination you are given a limited time. Also, if you do the integration or if you evaluate a certain physical quantities, it may take time. So if you remember some of the results, you can do it very quickly as well as correct. So now let us take the results. So we are considering the infinite well problem, so one-dimensional problem. Now here this is one end of the well is 0 and the another end is here. So this is one case. This is asymmetrical. So in the asymmetrical problem, you know the ground state wave function. So psi 1 is equal to square root of 2 by L sin pi x by L. So this is one dimensional the ground state wave function. For any nth state, psi n is equal to square root of 2 by L. Here there is a psi n pi x by L. So you must know the wave function for the one-dimensional box problem, asymmetric well problem. Now here, let us calculate the value of the probability. So probability is between any two limits. So here we consider P1. P1 is 0 to L by 4. So this is equal to integral. Actually, you define the probability, which is equal to psi star psi dx are the limits A to B. Probability of finding the particle between A to B. So here 0 to L by 4, you substitute this value of, if you want to calculate the probability of finding the particle in the ground state, you have to choose psi as a ground state wave function. You know psi star, since both are real, you can just multiply and you have to evaluate the integral. The limits 0 to L by 4. You are asked to find the probability of finding the particle in the ground state between the limits 0 to 4. So between 0 to 4, if you calculate, you have some value. That value is calculated as 1 by 4 minus 1 by 2 pi. So this result was already calculated in my previous lecture. You can refer back the previous lecture and you can find this value. So you know the method how to calculate P1. That was discussed earlier. Similarly, so this is P1 and this is P4. P4 are between the limit 3 L by 4 to L. So both are equal. You can see P1 and P4 are equal. Similarly, this one P2, P3. This is calculated as 1 by 4 plus 1 by 2. So you remember this value. So once if you remove this value, if you want to calculate the probability of finding the particle between say L by 4 to L, just add P2 plus P3 plus P4. So once if you add these three values, you can find the calculate the you can find the probability of finding the particle between the limits L by 4 to L. So that can be done. Similarly, you can find the expectation value. Expectation value of x, if the state is ground state, which is calculated as L by 2, and here, so here all the results are by choosing ground state. For the ground state we have calculated. For the expectation value of x square is equal to calculated as L square by 3 minus L square by 2 n square pi square. The expectation value of x cube is equal to this value. So these values are already calculated in the previous lecture. Then for a linear harmonic oscillator problem, the general wave function psi n, the wave function for the nth state is like this is n normalization constant e power minus 1 by 2 alpha square x square. This Hermite polynomial Hn of alpha x. Now here it is we can calculate it very easily. This is expectation value of h is 0, and for the ground state for x square this is 2n plus 1, x cube is 0, because all the odd functions it is 0, because this is a definite parity. So for if the function is x cube and etc., the odd function this will be 0, and for x square we have some value, x power 4 we have this value. Now if we take the ground state of the hydrogen atom, for hydrogen atom psi 1 is equal to 1 by square root of pi a naught cube e power minus r by a naught. This is a naught is the Bohr radius. Now here if you calculate the expectation value of r, this is found to be 3 by 2 a naught. Expectation value of r square is 3 a naught square. 1 by r is equal to 1 by a naught, and 1 by expectation value of 1 by r square is equal to 2 by a naught square. The expectation value of z is equal to expectation z is equal to r cos theta. So this is the expectation value, which is calculated as 0. Now we remember all the results so that you can do these problems easily. Now let us do some applications for first order correction. First order correction, the expression is W1 is equal to m h prime. So this is your expectation value of h prime in the state m. That is your first order correction. Now here this is the same meaning. This is the inner product of um comma h prime u. So this is the inner product. So you can either express in terms of the Dirac notation or in this scalar. This is this notation is the scalar product notation, um comma h prime um. Or in the integral notation, this is psi. The meaning is the same, psi m star h prime psi m dx. So all are having the same meaning. Using the Dirac notation or using the bracket notation, this is scalar product. This is called um comma h prime um. And this is a integral psi m star h prime psi m. This is integral notation. But in all the cases, the limit of the integration is the limit of h prime. That is important. The limit of the integration is the limit of h prime. Now, first let us discuss the one-dimensional problem, one-dimensional box problem. Between the limit 0 to L, h prime is b. So the limit of the integration is 0 to L, because this is the limit of h prime. So W1 h prime m m. The meaning is integral psi m star h prime psi m dx, and the limit is between 0 to L. This is important. Now you substitute for psi. This is a one-dimensional box, and for the mth state, if you consider the mth state, and the psi m is equal to square root of 2 by L psi m pi x by L dx. So this is the mth state wave function. The particle is in the this potential there. Now here h prime is given. This is a constant. So you substitute constant here. That constant b can be taken outside from this integral. You can substitute psi m and psi m star. So square root of 2 by L into square root of 2 by L. That constant can be also taken outside. The remaining part is sin square m pi x by L. And you know the value of this integral. This value of this integral is L by 2. This is the standard value. So once you substitute this value, you will get it. So this is your the first order correction unit. So this can be done the other way also, because this m h prime m, you substitute for h prime is equal to b here. Since b is not an operator, is a constant that can be taken outside. B m m m is equal to 1, because they are orthonormal functions. So this is equal to 1. So b into 1. So this can be either you can use integral representation or on this Dirac notation you can do it. So if you use Dirac notation, you can do it very easily. Now you consider another problem. Between 0 to L by 2, only the h prime is b. So 0 to L by 2, you have easy. And so in that case, what is your first order correction? M H prime M, and H prime is B N M, and what is the expectation value of M? Expectation value of M between these limits 0 to L by 2, which is equal to, that is important. When X lies between 0 to L by 2, then the expectation value is found to be 1 by 2. So that can be, you can do the integration, you can calculate this value by using integration or by using this thing. The expectation value between the entire limit 0 to L, it is 1, but between 0 to L by 2, the probability is only 1 by 2. So you can M. So this is a this value is found to be half, so B by 2. Or the correction, first order correction is equal to write down the constant B into the probability. So using this idea, you can easily calculate B into probability. Probability is for the limits. Here the limits is 0 to L by 2, so this is half. The previous problem, the probability is 1 because the limits is 0 to L. So the probability of finding the particle between 0 to L is 1. So B into 1. So this previous problem, this is B into 1. But here the probability of finding the particle between 0 to L by 2. So therefore, this is equal to half. So B into half. So you can do it very quickly. Now you consider another type of problem. Here the perturbation is given like this. H prime is equal to V naught when X lies between 0 to L by 2. And H prime is 2V0 between L by 2 t. So your the expression W can be split into two parts. One is between 0 to L by 2. This is M V naught M. Another is between L by 2 to L. So here the potential is 2V. So here this is a V naught, here 2 naught. Now here the constant V naught in the probability is half. Alright. Here the constant is V naught. What is the probability of finding the particle between L by 2 to L? This is half. So now add to this expression, you will get 3 by 2. Now you consider another case. H prime is equal to V naught. If it is X lies between 0 to 3L by 4 and 2 V naught between 3L by 4 to L. So here first between these limits this is V naught and the probability is P1, and here plus 2 V naught into the probability is P2. What is P1? P1 is the probability of finding the particle between 0 to 3L by 4. 0 to 3L by 4 we have already given the table. So you already calculated this one. Yes. So from here 0 to 3 by 4, you add these 1, 2, 3. You add all the 3 because here P1, P2, P3 are given. So if you add, you will get that result. So this is a half plus 1 by 4 plus 1 by 2 plus 2 V naught into 1 by 4 minus 1 by 2 pi. So if you add, you finally you will get it. So that can be easily done. If you remember the probability between the two limits, that can be easily done. Otherwise we have to calculate. The next problem. Now H prime is so far we have discussed a constant perturbation. Here H prime is proportional rate, so this is a linear perturbation. So between X to L, the limit H prime is proportional to L. So H prime is equal to Bx. So this is a constant. B is a constant. So what is the first order correction? The expression is M H prime must be replaced by Bx. Bx M. B can be taken outside. M X M. So this is B into expectation value of X. So that is the expectation value of X. So you can write like this. What is the expectation value of X? That is that can be calculated. This is found to be L by 2. You can do it very easily. So this because the table also we already given from the results that you have calculated earlier, you can directly substitute L by 2. Otherwise, you have to evaluate because expectation value of x means what? This is equal to integral psi star x psi dx between the two limits. So the limits are 0. So just substitute the psi star x and you can evaluate this how to be evaluated. Or if you remember the result, you can directly write down the result. So this is your W. And in general, H prime is proportionally x power n. Then this is a W H prime m. This is x power n. And B into x power n. This is a H prime. So you just you can find this value x power n is equal to what? X power n. This is equal to integral psi star x power n psi dx. Between the limits 0 to n. So you can evaluate this expression. Now let us take a problem. So you take this as a homework and you calculate this. So this problem. Now you take the next problem. Consider a free particle confined to a box 1D and the limits 0 to n. Now uniform electric field is applied along the x-axis. Find the first order correction of the energy of the first 3 states. So now here this is a potential well, a particle of mass m is here, the charge is q. So once if you apply electric field, then this is a q e, F is equal to q e actually. F is equal to charge into electric field. And the electric field along the x direction, therefore you write down magnitude here e and the unit vector is. So QEX. And work done is equal to 4 star F dot S. So QUX dot x into unit vector x. Fine. So QUX. So this is your H prime. So H prime is equal to QUX. Therefore W1 is equal to M H prime M. H prime is equal to QUX here. And Q is a constant term that can be taken outside. M H prime M. Now let us evaluate this expectation value of x between the limits 0 to n. And for the problem, one-dimensional well problem, this expectation value is already calculated as L by 2. So if you remember the value, you can directly write down the expression. So that you can do the problem very quicker. So you can do it quickly. You can do it do this problem. Now suppose for the 3 states, first state for the unperturbed state is E1. Because this energy expression is proportional to n square. So for the second state, this is 2 square, this is 4e, and this is 3 square, this is 9. So the ground state is E1, and this is 4 times E1, this second state, 9 times E1, this third state. This is the before the perturbation. But here the first order correction is independent of n. You have only a constant term. So there is a uniform shift in all the 3 levels. E1 plus QE L by 2. Here also QEL by 2. So there is a uniform shift. So this after perturbation this is here. Then the next problem, linear harmonic oscillator problem. Here H prime is proportional to x. That means H prime is equal to x. So first order correction, M H prime M. So this is the expression. Substitute H prime which is equal to Bx. B is a constant that can be taken outside. M H M. Now here this is your expectation value. For the harmonic oscillator problem, the expectation value is equal to because these 2 states are well defined parity and this is odd function, so that for this is. For the second problem, H is proportional to x square. That means H prime is equal to Bx square. This is the quadratic perturbation. So if you want to calculate W1, you have to use this expression. Substitute for H prime. This is Bx square, B can be taken outside. So M x square M. So this is the expectation value of x square. And we have already discussed this problem. This is equal to H prime is equal to 2m omega 2m plus 1. Here we are using capital M for mass because already we are using the symbol M here. It's a quantum number. So H cross by 2m omega into 2m plus 1. For the ground state, m is equal to 0. Substitute m is equal to 0. This expression is equal to b H cross by 2m. So this is the ground state, first order correction to the ground state. If H prime is equal to dx square for the harmonic oscillator problem. Now we take another problem. Consider a free particle confined to one-dimensional box. X lies between 0 to a. It is subjective to perturbation. Dx is equal to b naught into cos pi x by a. X lies between the limit 0 to a by 2. Find the first order correction to the ground state. So psi 1 is given. W1 is m h prime, and you substitute h is equal to, so the integral representation, this is 0 a by 2 psi m star h psi m dx. Substitute for h is equal to b naught into cos pi x by a, and you substitute psi m star, this is the ground state. You substitute back here root 2 by a into root 2 by a, so the 2 by a can be taken outside as a constant, and the remaining, the functional part is sin square pi x by a. Here there is v naught cos pi x by a. Again the v naught is a constant that can be taken outside, so 2 v naught by a. The final expression is, the limit is 0 to a by 2, which is this the limit, limit of the perturbation is from 0 to a by 2. So this is 0 to a by 2 sin square pi x by a cos pi x by a dx, and this can be integrated. So this cos can be expressed d of differential of sin pi x by a divided by pi by a. Now this can be expressed as sin cube by 3. So now you substitute the limits, we will do this. So the first order correction can be easily evaluated for this problem. Then we take another problem. Consider a particle of mass m in a potential. This is unperturbed potential, and this is perturbation g cos kx. So what is the change in ground state energy compared to the harmonic oscillator potential? This is the unperturbed potential energy, and this is a perturbation. Now, so this is perturbation g kx. So the first order correction is given as W1 is equal to mh prime n. This is you can use any symbol. Instead of m, I am using n here, and n h prime n. And if you put n is equal to 0, this is the ground state growth function psi 0 alpha by root pi square root of alpha by root pi e power minus half alpha square x square. This is the ground state growth function of the hydrogen atom. Linear harmonic oscillator. So substitute these values of psi star, psi naught star, h prime, psi naught dx with the limits 0 to infinity. Then this the square root of alpha by root pi into square root of alpha by root pi, and that, so within the alpha by root pi is a constant, can be taken outside. In the remaining part, e power minus half alpha x square into e power minus alpha x square, that is combined to e power alpha square x square. Here in this function g cos kx, I am putting here, and g is a constant that can be also taken outside from this integral. So this is the, so this is actually for a cosine Fourier transform. So using this Fourier transform technique, this is standard value. This is also available. If you remember, you can do it very quickly. So this is the constant into square root of pi by alpha square e power minus k square by 4 alpha. So this is a cosine Fourier transform. So actually this is a Gaussian type, Gaussian expression, and this is a cos kx. So using the Fourier transform, you can obtain this expression very easily. So now finally you have this result. So this is your first order correction. The important thing is you must remember this standard integral, the Fourier transform expression. If you know the Fourier transform of a particular function, if you remember this result, you can do this problem too. The next problem is, a rigid rotator in a plane is acted in by perturbation. The perturbation is here. Calculate the first order correction to the energy of the ground state from phi psi of phi is equal to 1 by square root of 2 pi e power I m pi. M is the quantum which is 0, plus or minus 1, plus or minus 2. Now here for the ground state, m is equal to 0, therefore and the psi corresponding to ground state, and that expression we substitute m is equal to 0 is equal to 0. So this is the psi ground state. So W1 if you want to calculate, your psi n star v and h prime is given, h prime is here. This is given, you substitute this value here, and psi n star psi n, and psi n, this is the ground state which is equal to 1 by root pi. Again there is a 1 by root pi, so that can be taken outside from the integral 1 by 2 pi, and there is a constant v0 by 2 is here, so that can be taken outside from this integral. So the remaining value is equal to 3 cos square pi minus d pi. So that integral can be split into two parts, and the first one is the constant 3, and if you evaluate this integral of cos square pi d phi from the limit 0 to 2 pi, this value is calculated here, and here if you evaluate this integral, this is 2 pi, and you simplify, you will get the v0. So this is the first order correction to the energy. Next problem. Two identical bosons of mass m are placed in harmonic potential. This is harmonic potential of m omega h square. The boson can interact through the interaction V1 2. So this is perturbation. Find the ground state energy of the two bosons. So now here we are using this one. E power minus x can be expanded because x is small. This e power minus x actually okay, when x is small, you can write this 1 minus x. 1 minus x whole power n will be 1 minus. This will be used for following discussions. So we write down this result. Now the correction to the energy term, which is h prime, n h prime. So this is the correction to the expression, and n h prime is given from the column. So this is v naught m omega e power minus m omega into x1 minus x2 square whole power 4 h cross. This is given, and so the h prime alone may be expanded in series because e power minus using this one, you expanded in series, and this is a v naught because you written up to the first power. So this will be v naught into minus v naught m omega by 4 h cross, and this expression. Now let us find the expectation of h prime. This is a constant term, so therefore you will have only v naught. Here v naught minus v naught m omega by 4 h cross, and this is expectation value of x1 square, expectation value of x2 square, and this is minus 2 times expectation value of x1 x2, and this can further be expressed by expectation value of x1 x2, and expectation value of x is 0 and expectation value of x2 is 0. Therefore this term will be 0. Therefore so because this is a harmonic potential of harmonic x square term, so expectation value of x is 0, expectation value of x2 is again 0. Now let us calculate the h prime. This is a v naught minus m omega by h cross. What is expectation value of x1 square? We have already calculated. This is a h cross by 2m omega into 2n plus 1. The result was given earlier, so you just take the result. Otherwise you have to evaluate this integral. That's why you must remember certain results so that you can do the problem very quicker. So this is h cross by 2m omega into 2n plus 1. Similarly for the x2 square also, expression like x square is also this way. And for the ground state, you have to choose n1 is equal to 0 and 2 is 0. So you substitute n1 is equal to 0 and this 0, and this expression value of h prime is equal to v0 minus m v naught m omega by 4 h cross into, you put n is equal to 0, this is h cross by 2 m omega, h cross by 2 m omega. You simplify this one, you will get this. And if you want to calculate the total energy, the total ground state energy, So what is the ground state energy of each particle? Half h cross omega. There are two bosons. Two bosons can occupy in the same state. So two bosons. So you multiply half h cross omega into 2. So this becomes h cross omega plus the correction. The first order correction. The first order correction is we have calculated. So if you add these two, we get the ground state energy of this system. The next problem. A helium-like atom with the electron-electron interaction is replaced by Hooke's law force, described by the Hamiltonian H is equal to minus h cross square by 2m, del 1 square plus del 2 square, and half m omega square r1 square plus r2 square plus this term. This minus l by 4 m omega square modulus of r1 minus r2 square. So this is your perturbation. This is a since it is a Hooke's law, so this is a harmonic oscillator type problem. So this is your h prime. H prime is equal to lambda by 4. This is given r1 minus r2 mod square. If you expand this one, you will get this term. So the expectation value of h prime is equal to minus lambda by 4 mu square. This expectation value of r1 square, r2 square minus 2 r1 r2. As we have discussed earlier, expectation value of R1 and expectation of R2 is 0 for the harmonic oscillator because this it obeys Hooke's law. Since it obeys Hooke's law, F is directly proportional to x, F is equal to minus kx. So this is a harmonic oscillator type. So this will be 0. So you have to evaluate expectation of R1 square, R2 square. This is already given for the harmonic oscillator problem. For the first particle you have this energy, this other particle you have this energy. And for the ground state, N1 is equal to N2 is equal to 0. So if you put N1 is equal to N2 is equal to 0, then H prime is found to be minus lambda by 4 H cross omega. So the exact energy if you want to calculate, so the first particle the energy is half H cross omega, that is for the ground state. For the second particle you have half H cross omega, which is the ground state energy, and then the interaction energy is minus lambda by 4 H cross omega. So if you add, you will get this. Now we take the next problem. Consider a quantum system with Hamiltonian. This is Hamiltonian is given kinetic energy term for the first particle, for the second particle, and this is the potential energy for the first particle and the second particle, and this is the perturbation. So what is the exact ground state energy of the system? So if this is H prime is given, W is equal to expectation value of H prime. This is lambda of expression value of x1 square plus x2 square. And this is this problem you already done. You know the result of this one, expression like x1 square. Similarly for expression like x2 square, result is also known. If you add these two, you will get the first order correction. If you put n is equal to 0, you will get the ground state, the correction to the ground state energy. And the total energy is equal to, there are two particles. One particle is having h cross omega, for two particles you multiply by 2, which is h cross omega, and this is your correction term. So finally you will be this. Now let us do the problem using a Dirac potential, because this type of problem you can this is often asked in the net examinations. Now here the particle of mass m confined to a potential. This is Vx, this potential. This is the potential well. This potential well. The perturbation is given like this. This is a Dirac delta potential. Now the solution is, what is the first order correction is expression of h prime, so which is psi star h1 psi 0. So this is for the ground state, so we are using psi 0 star, and the limits are from 0 to a. The limits of the perturbation is 0 to a. Now psi 0 is for the potential, the particle is infinite. So this is square root of 2 by a sin pi x by a. So you substitute psi 0 star and psi star. So the constant term is taken outside, the remaining value sin square pi x by a, and the perturbation is this way. You may take a V0 also outside. Now let us use how to evaluate the Dirac potential. F of x delta of x minus c between the limits a to b where C lies between A to B. This is equal to FC. So using this value, using this the evaluation of the delta function, the integral of the delta function can be evaluated by this method. So using this, here x minus a by 2 is within the limit 0 to a. So the x may be replaced by a by 2. That is the result. So this x must be replaced by a by 2. X must be replaced. So this is the value evaluated x is equal to a by 2. So to substitute this value, we will get 2a by d. So this is your problem using delta potential. Now another problem using delta potential. Consider a particle of mass m confined to a potential. So this is the three-dimensional box. So x lies between 0 to a, y lies between 0 to a, z lies. So this is a cubical box problem. It is subject to a perturbation. The perturbation is given like this: delta x minus 2, y minus 2. So this type of potential is given. Now what is the ground state wave function of the particle in a box? Square root of 2 by a whole cube sin pi x by a sin pi y by a sin pi z. So this is the ground state wave function. So this is the first order correction. This is the expression. So first write down psi star ground state, h prime psi, and dx dy dz. The limits are from 0 to a. The limits are from 0 to a. Now you substitute h prime. H prime is once you substitute h prime, and if you take the constant terms outside, 2 by a whole cube d naught can be taken outside, and 0 to a sin square pi x by a delta function of x minus a by 2 dx, 0 to a sin square pi y by a delta of y a by 4 dy. So you write down the x part alone, y integral separately, z integral separately. Now let us evaluate this integral. So this integral is a standard value. So you substitute this value, and here you have to use the definition of the integral of the delta potential. So here y must be replaced by a by 4. Here x must be replaced by a by 2. Then you have to evaluate this value. So once you evaluate, we will decide. So using this is the definition for evaluating the delta potential. So this is the integral using a delta function. So use this one, you can easily evaluate this integral. Next problem. A one-dimensional box of length A contains 3 particles, each of mass m. The interaction between them is Vx, 2 is equal to this. So this is a delta of x minus 2, which is slightly different. So calculate the ground state energy up to first order. Now here, this is a two-dimensional problem. So psi 1 is equal to psi 1 of x and psi 2 of x. So this is a box problem. So this is particle 1. For the particle 1 you have one, for another particle you have another wave function. So this is a one-dimensional problem, but this is there are 2 particles. So this is a one-dimensional box. Now the first order correction is equal to integral expectation. This is the h prime between psi 1 and psi 1, and you substitute psi 1 and psi 2 here. And how to evaluate this integral? First you take this part, sin square integral sin square pi x 2 by a sin of delta of x minus x2 dx. So you take this part first, and after evaluating you can evaluate the other part. So here, what is x2? Yeah, this is x2 must be replaced by x1. So already there is a pi square sin square pi x by a, already there is one. If we evaluate this integral, this is sin square pi x1 by a. Now this is integral is evaluated between 0 to a and for dx. So now this can be evaluated. So the constant term can be taken outside, and 0 to a sin power 4 pi x by a dx1. This is can be easily evaluated like this, because we have a standard expression 0 to a sine power n pi x by a dx is equal to, and n minus 1 by n 0 to a sine n minus 2 by x by a dx. Since here n is equal to 4, 4 minus 1 is 3, 3 by 4, so we are using 3 by 4, and this is 0 to a sine square pi x by a. So sine square pi x by a dx is equal to a by 2. This is also a standard value. So using, by remembering some standard integrals, you can evaluate this integral very easy. So finally, this the first order correction is found to be W1 is equal to. So first we have discussed the theory, perturbation, time independent non-degenerate case perturbation theory, and we obtained the first order correction, the expression for the first order correction in energy, and we found the expression for the first order correction of the wave function. We have calculated the expression for the second order correction. So how to calculate this expression, how to calculate the second order energy level, that will be discussed in the next lecture. So for the degenerate case also we will take this problem in the next case.